Uh, Today's lecture is on behavior cloning, specifically on diffusion policies. I'm sorry I'm not able to do this in person. I was on a trip and I caught a cold. So I'm going to do only a 1 hour lecture and on Zoom, and I'll give you some reading material or watching material for the next hour. So what's the topic of interest? The topic of interest to us is the following. It's this area called robot learning from demonstration, and it's been around forever. It was in fact the earliest robots had these ideas were in use then. So I here's the abstract of a paper, recent review paper by these folks. And they have this statement: in the context of robotics and automation, learning from demonstration is the paradigm in which robots acquire new skills by learning to imitate an expert. And then they abbreviate this as LFT, learning from demonstration. So the choice of LFT over other robot learning methods is compelling when ideal behavior can be neither easily scripted, as is done in traditional robot programming, nor easily defined as an optimization problem, but can be demonstrated. So let's look at the variations on this theme. So here is the first one. It's called kinesthetic teaching, and this goes back to the earliest days of robotics. So basically what you do is you make the robot go through the movements, and then you just record that trajectory and then you replay it. So an example of when this might work is, for example, you want to have a robot do a painting task, and you just make it go through the movements, and then it just replays it repeatedly in a factory setting. Second example is teleoperation. So here, this is B in the middle. So what do you see here? Here there's a person with some controller, and what he or she is trying to do is to make the robot go through certain motions while observing the robot do the task. So you might essentially be controlling the joints of the robot so that the robot picks up an object, moves it around, what have you. So this is teleoperation. Now, teleoperation has existed for a very long time. In the early days, it was used basically for working in hazardous environments. So in a hazardous environment, you have a robot, let's say in a nuclear reactor kind of situation. And then there's a person working remotely, and they are manipulating the robot in this remote way in a safe environment. And then, of course, the robot is going through exactly the same motions that the human is going through. Now, in this process, you can collect trajectories, and then subsequently you can use those trajectories in a form of supervised learning to train a new policy. And that's going to be the bulk of today's lecture. Okay. Then approach C is passive observation, and this is what I call genuine imitation learning. So normally, how do children learn uh, from observation? So there isn't an adult who's controlling their brain to make them go through the entire sequence of actions. I mean, that's the teleoperation thing, but that's not what we do not teleoperate our children. What we do is we might show them a task. For example, we might show them how we make an omelette, right? Or assemble some Lego pieces together. And the child observes what we are doing and then learns from that. So this is sometimes called imitation learning because children have a strong urge to imitate. Now, this is a harder version of the problem than what you saw in A and B, because you do not uh, have the same body. So you do not have access to the full state, right? The child who's imitating the parent doesn't have access to the full state, like what are the mental commands being issued by the parent and so on and so forth. So it's an incomplete knowledge that you have to make use of. And then there is a shift in the embodiment because the person's body is not the same as the child's body, or the person's body is not the same as the robot's body. So all this makes it more complicated. The advantage of this approach is that With this, you have lots and lots of data because you can take all the 156 million hours of video on YouTube, for example, and use that for training a robot. So we will study this approach, but in the next lecture. Okay, so this is what we'll call visual imitation. So today's lecture is primarily about B, and this has become a very popular approach in the last few years. And one of the reasons is that there's been a kind of a breakthrough called diffusion policy, which has enabled a very good machinery for taking a lot of robot trajectories collected by teleoperation and then use that to train a policy. So it's a supervised learning setup. Supervised learning, we know, works very effectively in, for example, in tasks like computer vision. So this is basically training, converting the task of robot uh, training a robot to do manipulation to a supervised learning task. Any questions so far? And in the last lecture, we were talking about reinforcement learning. So there, the setup is that you specify the task by some kind of a objective function or cost function, and then reinforcement learning is just a way to find and to optimize it, to find a policy which optimizes that. So there, the basic insight is that the specification of the task is through a cost function. In teleoperation, the specification or task is just copy the sequence that humans did at training time. So it's a much easier way to specify a task. Okay, so I'll talk about this paper, diffusion policy. This is from Shurun Song's group. She was originally at Columbia and then she has moved to Stanford. And there are a couple of papers. The first one is RSS 2023, and the second one is at IJRR 2024. So this later paper is in collaboration with people at Toyota Research Institute, and then they took this approach and applied it to a lot more tasks. So, but the core ideas are there in the first paper. So, what I'm going to do is to give you a little flavor of this by just playing a video. But first, let me go to the next slide. So, this slide is like the abstract of this paper. So, these are their claims of fame. Diffusion policy, a new way of generating robot behavior by representing a robot's visuomotor policy as a conditional denoising diffusion process. So blah, blah, blah. They're testing it on a variety of different manipulation tasks, and they find that it does much better than the various alternatives. So what I'm going to do is I found a lecture on YouTube from the authors of this approach, and I'll play a little bit of that because that has demonstrations of what tasks it can do.
Thanks, Alex, so much for introducing me to the audience, and thanks for inviting me to. It's a visual motor policy that we can deploy to our robots. Therefore, regardless of how the policy is trained, if the representation of the policy itself is not expressive enough, you can easily bottleneck all of the approaches. Today, I'd like to convince you that with sufficiently powerful policy representation, even the simplest learning paradigms like behavior cloning can work very well. And here's some examples of diffusion policy trained on a variety of tasks directly from pixels. And you can observe some interesting behaviors, for example, recovery from failure and robustness against perturbations and occlusions. So what is diffusion policy? I think many of you might be familiar with diffusion model for image generation. Here, we're using a similar idea to generate robot actions. So in diffusion model, well, like for example, like a Midjourney is a text condition image generation model. So the input is text, and then the output is an image, and then the image is generated using a diffusion process. And in our case, policy's input is image, and the policy's output is a sequence of actions that is being generated using diffusion model. And here in the bottom, we have an example that's shown as a sequence of 2D n factor positions, which is the action space for this task. it's a mirror of the simulation push-T task. But the method can generalize to pretty much any dimension or degree of freedom for your robot. Yeah, so concretely, we start with Gaussian noise, and then neural network is trained to predict the gradient of action to remove the noise conditioned on robot's visual observation. After a few of these denoising steps, it will give us a clean and executable action trajectory. And the whole denoising process is our policy representation. It repeats at 2 Hertz, resulting in a reactive closed-loop behavior. So with this simple formulation, diffusion policy is able to simultaneously address a number of challenges in policy learning. And today I'll highlight 3 of them. First is the capability of representing action multimodality, which in this scenario, there are multiple valid actions for the same observation. For example, on the left, we have this push-T example. The goal is for the blue dot is like the robot. And then the goal is to push this gray T into this green area. So at this exact moment, there are 2 perfectly equally valid actions to take. One is to go around the top of the T and push it. Another one is to go from the bottom to push it. In fact, both of these modes exist in our training data. And for a human demonstrator, depending on our mood, we might randomly pick one on the top or one on the bottom. And we can imagine that if both of these data exist in the training data set, if your polished representation is a function, then it will get very confused, which is actually really the assumption of a lot of the prior behavior cloning or polished representations. So as we all know, neural networks, feed-forward neural networks, is a universal function approximator. So it's really powerful for representing function, but it can also only represent functions. And here, the difference is that now what we want to represent is a bimodal distribution instead of a function. Given one input, sometimes we want to go on one way, sometimes we want to go the other way. And if we represent it as a function, and let's say if we train with something like L2 loss, then the policy will learn to take the average between, to minimize the distance to all data points. As a result, it will learn the average of all data, and then it will probably go through the middle. And imagine you're driving a car, you're trying to avoid a tree. Then if you do like action regression, then like it will go straight through the tree and then crash. Similarly, so I guess one of the surprising things is that this action modality, of course, we can construct this very specific case where action multimodality is important, but it's actually surprisingly common. And my observation is that a lot of these action multimodality comes from pulsing behavior. For example, in the middle, here is the real version of the push-T task. The task is not only to push this T into the center region, but also after it is done, the robot needs to decide, now I'm done. I need to go to the upper right. There's a circle I draw on the table. That's the exit location. And you can imagine there are many instances during this episode where the T is somewhere there, somewhat inside, and but so like anytime the policy can exit, but also you can just spend a little bit more time refining the pose of the object. And humans sometimes, depending whether I'm tired or not, will make very different decisions at different points of whether this is good enough or not. And pretty much that creates a huge amount of action multimodality. And if you don't use a representation, for example, like diffusion policy, then the policy will struggle. So previous method often attempts to approximate this multimodal distributions with categorical distributions or mixture of Gaussians. Which Gaussian you pick, and then you're also instead of a single step, which turns out to be critical to ensure temporal consistency among output actions. And finally, diffusion policy is also quite stable to train, which is also essential for robotics. Especially this stability is especially compared against energy-based models, which I'll talk about later. And this, because for robotics, checkpoint selection often requires very expensive real-world evaluation. It's not like a metric that you can log during training. So if you have to select, if for example the model is easy to overtrain or either overfit, or if the model will easily diverge, you might not even know during training. and then you have to run every single checkpoint on the robot to figure out which one is good. That will be a very tedious and very error-prone process.
So I want to stop that video, and I want to get back to my slides. Okay. So what you learned so far was the value of the so-called the diffusion policy, which is a way to combine a lot of demonstrations. So you collect a lot of teleoperation demonstrations, and then you make them, and then you sort of put them all together into this diffusion policy. So so it's a particular application of these diffusion model-based generative modeling. So what I'm going to do in the rest of the lecture is to actually give you the general some insight into the general theory, and then the diffusion policy is just a special case of this. So it's a special case of diffusion models, and in specifically conditioned diffusion models, and the conditioning here is on the observation. So we must try to understand the general approach first, and in the lecture that I played like 5 minutes, 10 minutes worth. I mean, that was kind of glossed because it was assumed that the reader knows that. So, but this is what I'm going to focus in the rest of my lecture. And what I've got here are slides from a tutorial on diffusion modeling, which was presented at CVPR a year or a couple of years ago. And so I'm going to take you through that. Okay. So what's the problem we are trying to study? So this is the area of what's called generative modeling. And the concept of generative modeling is the following. You're trying to find a probability distribution from which you can sample. So for example, you want to have a probability distribution over the space of all images. So this is what is indicated here by this person with this neural network in his head. And from that model, what you can do is sample. So you can generate one sample, you might get a cat, or you generate another sample, you might get a dog, a third sample, you might get Jennifer Aniston, and so on. So imagine that there is a space of all possible images, and then there is a probability distribution over all spaces. Because if you think of the set of functions from say, let's say if you consider, say, a 4x4 image, right? So a 4x4 image has 16 pixels. Now, if each pixel can take one of 256 values, then you have 256 to the power 16. So these are the set of possible images that there are. But this is not the set of natural images. Natural images are very, very sparse in this set of all possible images. And what you want is this function, this probability density function over the set of natural images from which you can sample. And this function is very, very important and very useful, because when you consider conditional version of it, you can use it for denoising, you can use it for generation, you can solve it for like a huge variety of problems. And so this whole area of generative modeling, which is finding the probability distribution over, let's say, the set of images, is an exciting area, and one in which a lot of progress has been made. In the early era, this was the area was dominated by GANs, and GANs had lots of problems, and I don't want to go into those. But today, I would say that there are then today these denoising diffusion models seem to be winning this battle, at least in the context of images. In the context of language, autoregressive models, those are also generative models. So they seem to be popular there. Uh, Theoretically, very important idea is that of variational autoencoders, which in fact, if you want to understand the theory of diffusion models, you have to go back to understanding a little bit of the theory of these so-called VAs, variational autoencoders. And let's see how far I go in the next half hour, but I'll give you references so you can read up and understand this better. So let's first go through some examples of what diffusion models can do. So I'm going to use examples of images, but I mean, all these ideas just exactly transfer over to the setting of policies. Okay, so these are just examples of images that can be produced by these diffusion models. So these images can be, we can do condition generation. So for example, I can condition by some text like lion or tiger or an astronaut on a bicycle. And then you synthesize the image conditioned on this text. And that's how these models like DALI and Imagen and so forth operate. In the context of robotics, what are we going to do? The conditioning is going to be on the basis of observations. So the observation might be some image observation, for example, or some proprioceptive observation. Okay, so these are some examples of text to image generation. Uh, okay, so let me try to illustrate the core idea of diffusion models, and it's a very elegant and beautiful idea, and it goes back to ideas in sort of probability and in physics nearly 100 years ago. There's this idea called there's someone called Paul Langevin, and they are these so-called stochastic Langevin models, and that's really the intellectual root of this idea. But let me explain to it in a much more pragmatic sort of a way. What are we after? We are after a generative model of images, right? So that's our goal. So how do we get, now a neural network is a function. So if you give a neural network one input, it's always going to give you one output. So if I want to get a distribution, how can I get it? I can't, right? A neural network always gives you one output for one input. So the only way to get a distribution over a set of images is that the input also must be a distribution. So for example, the input could be a Gaussian noise, right? So in this case, if you see on the extreme right, there is a Gaussian noise image where every pixel is a sample from a Gaussian. So what we can do is we can generate samples of Gaussian noise. That's very easy to do. And then this neural network, this so-called generative model, what we do with that is we feed it these different inputs, which are different realizations of this Gaussian noise model, and then we'll get different outputs. And those different outputs, what we want them to be is over the set of possible real-world images. So you might get cats or dogs or people or chairs or bicycles or what have you. So our job is to train this neural network, which when given as an input some noise image, outputs one of the set of possible images. And essentially according to the probability distribution over the set of all images. Is the idea clear? I mean, just interrupt and ask me questions if this is if what I'm saying is not clear, because okay. So that's what we are trying to do. And that's been the goal for a while. So for example, these variational autoencoders, VAEs, that's how they are. They are trained in a particular way, but the way you use them is that you input noise and then the output is a sample. And because you will input different noise samples, the output will be different samples of images. Okay, now how do these diffusion models work? So in diffusion models, the idea is that we take we are going to have a so-called forward diffusion process and a reverse denoising process. So the forward process goes something like this. I mean, it's very easy to see in this picture. So we are going to have some image, like this image of this cat, and we keep adding noise to it, okay? And we keep scaling the original signal down. So you are trying to keep the energy the same, but you keep scaling down the original signal and you keep adding noise. So it becomes more and more noisy, and eventually it's like not distinguishable from noise in some way. So, but you do it in a series of steps. So maybe you do it in 1,000 steps. I mean, in this figure, it's like 7 steps, but it could be over like 1,000 steps. Okay. And now, and what do we train a neural network to do? We train a neural network to go in the reverse direction. So the forward direction is easy, right? It's just adding noise. Now, what we will try to train in is a neural network which can do the reverse denoising process. So the neural network, what it is trying to do is, given one of these images, its target is to get to the denoised image. And you know the target, right? Because we generated this example. So we took this original image and we added noise, and then we went all the way to this something which looks pretty much like noise. And what we are doing is we are driving the process backwards, which is to go from noise to this image of this this cat, or is it a dog? I'm not sure. Okay. So so that's so you train a model for doing that. And this model can, and of course, you will give it lots and lots of example such sequences. So you might start with an image of a dog or a cat or a person or a bicycle or a chair. And each of them goes through this sequence by which noise is added and it eventually becomes pure noise. And then you've got like a training data set, because for this sequence, you know what your reverse denoising process has to do. It has to get back to the original image. And so we train that model. And we train that model with many, many examples of images of cats, images of dogs, images of chairs, and so forth. And then at test time, so that's the training process. At test time, the idea is you just feed it a noisy image, a noise, which you just you can sample from a Gaussian distribution, and then you let it go with this neural network, which is going to generate these, do a series of these denoising steps, and then you'll get something. You might get a chair, you might get a cat, you might get a dog. Okay, so that's the intuition. And so now let's get more mathematical about this. The formal definition of the forward process is that that's illustrated here. So let's look at the math. So this is a Markov chain. You start from some initial state x0, then you go to x1, x2, so on. And this x sub t is basically an image which is indistinguishable from noise. What are you doing at each stage? You're adding Gaussian noise, and that is indicated by this this process. So what is this notation n? N is for normal distribution, right? So the normal distribution, so there is a distribution of the random variable x sub t. It has how do I specify a normal distribution? I specify a mean and a covariance, right? So the mean is xt minus 1. So you start for every pixel from the previous stage, okay? You scale it down a little bit by the square root of 1 minus beta t, and then you add noise. Okay, so this is the variance here, the variance of this Gaussian, and it's a diagonal matrix with this with every entry in the diagonal being this beta sub t. So every pixel is being independently. So with every pixel, you're independently adding a little bit of noise, and so that's what you're doing here, and you do that to get from x0 to x1, x1 to x2, and so forth. Okay, and then the concatenation of these processes is what you get at the end. Now note an observation, because we are dealing with Gaussians here. If you add a bunch of Gaussians, that's also a Gaussian, right? So Gaussians have this very nice composition property, and this is going to be helpful to us. Okay, so this is the forward diffusion process, and then if you crank through the algebra with these square root of 1 minus betas and so forth, I mean, that's what you get these terms, but this is not important. You can work through that. The intuition is pretty clear that each of them is a little Gaussian, but if you think of a big step, it's like a big Gaussian, but it's always Gaussians all the way. So what's going to happen? Essentially, the addition of noise is losing structure, right? So you can start out with some initial data, and as you are adding noise, over time, it's going to become something like start to look like a Gaussian, right? This should be intuitive. Okay. And now what you're going to do is you're going to learn to go backwards. Let me see if I have a picture which illustrates this better. Actually, I want to give you one intuition which is very cool, which is that why are we doing this breaking up into small steps? And it's to do with, if you think of physics, right? So suppose there is some liquid, and at the end of the lecture, I'll show you some video, and you drop some colored fluid in a liquid. Then over time, what happens is that it diffuses and then it becomes uniform. So there is some initial structure, and then it's getting lost over time as diffusion proceeds. We're doing something similar here on the images. Now, can we go backwards, right? This sounds crazy, right? Okay. But it sounds crazy, but if you consider a small step, going backwards is not unreasonable. Because if you think about physics, at any small scale, all the processes of Newtonian mechanics are reversible, right? Over a long time frame, entropy increases. But locally, over a very small moment of time, the processes are reversible. Okay, so I find this intuition very comforting, that the long step of going from signal to noise is not so easily reversible, but a micro step, like the step from x2 to x3, is adding a little bit of noise, so we might hope to recover the going from x3 to x2. And this is kind of an intuition which actually can be made quite formally precise with this whole theory of Langevin dynamics. Okay, so where are we going here? Okay, I'll show you. Okay, so this is another fun video I found, and let me play this. And so there is this genre of people who put up videos on YouTube, which is explaining the same concept at multiple different levels of explanation. So I'll play this video, and just the first two levels of explanation are not bad.
Let's learn about diffusion models. Diffusion models are a fairly new innovation in the world of deep learning. They are generative models that are being used in many different domains like audio generation or image generation. You might have heard of them with their use in DALL-E or Imagen, for example. Diffusion models can be used standalone like they did with Glide, or it can be used as part of a bigger and more complex model like it was done with DALL-E 2 very recently. Their inner workings are quite complex, so it could get a little bit confusing to understand how they work and how they are trained. That's why in this video, we are going to approach it step by step and explain diffusion models in 5 varying levels of difficulty, starting from the easiest one to the more complex one. Level 1. Diffusion models were inspired by non-equilibrium thermodynamics from physics. And as you can understand from the name, this field deals with systems that are not in thermodynamic equilibrium. For example, a drop of paint in a glass of water. The density of the paint after you just dropped it is very high in one spot and 0 in other parts of the water. By the laws of physics, the drop will diffuse into the water until it reaches an equilibrium. In the physical world, reversing this diffusion process is simply not possible. But with diffusion models, the goal is to learn a model that can reverse this process and bring the drop of paint to its original state. In other words, the drop being in one spot includes some information, and as the diffusion process progresses, we lose information. In our case, this information equals to clear images. So working backwards from this diffuse paint is equivalent to working backwards to a proper image. Level 2. Diffusion models work by replicating this diffusion process by adding noise to original images and later learning how to reverse this noise process. The noise is applied to the images following a Markov chain. What is a Markov chain? A Markov chain is a chain of events where the current time step only depends on the previous time step. So that means there are no cross dependencies between time steps that do not immediately follow each other. And this assumption of Markov chains makes it tractable for the noise adding to be reversed later. So at the end, a diffusion model is a Markov chain where in each time step, we add a little bit of noise to our image until the image only consists of noise, and later learning how to reverse this noise adding process. After it is trained, given only noise, this model is able to generate high resolution images. Level 3. So now that we understand what diffusion models do is basically add noise to an image, let's understand what it means to add noise to an image. There are many different types of noise, and the noise that is added in diffusion models is called the Gaussian noise. What is Gaussian noise? It is a noise that has the probability distribution of a Gaussian or normal distribution, given the different mean and variation values for this.
Yeah, I'll stop this here because you know about Gaussian noise. You don't need to learn that from her. Let me see if I can quit here. You have to stop share again.
The location and the width of the distribution.
Okay, so maybe that water droplet picture was helpful. So where were we? So now what we are going to train our neural network to do is basically this reverse denoising process. And okay, what's the connection here? If you want to understand this theoretically, what is going on here, what is being optimized, you really have to go back to these VAEs, variational autoencoders. I have a reference for that in the slide deck, but I'm not going to go into it. And where are we here? I'm going to skip all this. The final, even though the theoretical understanding is a bit complicated, the practical aspects of our intuition is very clear, I think. What you are training is this denoising network, which given an image gets you to a slightly less noisy version of the image. And this network here is, so there's algorithm 1 and algorithm 2. So algorithm 1, let's look at that. This is for training time. So you have so this epsilon network starts out being one which just is a Gaussian. And what you're doing in this training step is essentially training this denoising. So you're trying to, okay. And then at the sampling time, you're going to start from synthesize. First, you'll generate some. So why you get different samples is because you get different inputs. So you get different inputs, which are these samples from a Gaussian distribution. And then you run it through this sequence of denoising steps. And these steps, because they have different inputs, they will land up going to different endpoints, and these different endpoints will then look like different images. How you implement this? So there's a lot of lore. Earlier work used to be done with convolutional networks. Units were very popular. Today, like everything else, everybody is using transformers. And in the diffusion policy paper, they say that they started out with convnets and then later on switched to transformers. Okay, there's a detail on how you add the noise and how many stages. So here, there's a practical consideration when you are trying to use this for a robot policy. So note that you're doing all these steps of denoising in real time. So your robot is trying to move and you're trying to figure out what are the next steps. And to do that, you have to be running this several steps of denoising. So therefore, you can't really afford to do 1,000 of these steps. You have to do a relatively small number, and it has to be working really fast. So, so if you read the paper from Shuren Song's group, you will see that they managed to make all these details work out. So you're trying to do inference in like 0.2 seconds or something like that. So that and you output a sequence of actions, so you can start to execute those, and then you have some time in the meanwhile to be running this inference again and so forth. What happens to an image? Okay, this is also maybe a helpful thing, that in the forward diffusion process, essentially the high frequency information gets killed first, and then gradually it gets to the low frequency information. Okay. And then the denoising process, you can see that in the beginning, so this is the denoising starts from the noise and goes to this generating the sample. And so what's happening is that initially the low frequency content starts to appear, and then later on the high frequency content appears. So there are a variety of papers playing off on this theme. So it's almost the papers which are suggesting that you can think of it as an autoregressive process where initially the low frequency content is produced, and then the medium frequency content is produced, conditioned on the low frequency content, and then finally the high frequency content is produced. Connection to VAEs, yeah, there is theory there, but I won't get into. But I'll probably leave it here. Okay, conditional diffusion models. Okay, so conditional diffusion models in the context of image synthesis, the conditioning is very often on text. So, so these are examples. So, there's the text, a photo of a raccoon wearing an astronaut helmet looking out of the window at night. And then this is the image which is synthesized. So in the context of diffusion policy for robotics, what is the conditioning going to be on? So the conditioning is going to be on whatever is the observation. So the observation could be proprioception, it could be camera input. And then here are varieties of tasks, conditional. Okay, so how do we include conditions in the diffusion models? So basically, you have the standard forward process, reverse process. In the reverse process, you have the C. So the C is what you are conditioning on, and what we will see is for the diffusion policy, the C is going to be the observation. Okay, I think I'll end here, and let me stop share and maybe